Hello guys, nice to see you. So today we continue to consider topics related to ray optics, and the main topic which is planned to be discussed during this lecture is the formation of images by flat mirrors and also by spherical mirrors in different types of two different types of spherical mirrors. But before that, I would like to remind you, first of all, that this Saturday we will have the third midterm. Please be aware of that, prepare. So that will be chapter 12, 13, 14. No, it will be chapters 13, 14, 15, and 16. Yeah, most likely. But double check, this information should be available in the manual for the course. So be ready to log in, have access to internet, and be sure that you will not have some unexpected issues which will not allow you to pass the midterm. So also, I would like to shortly discuss three small topics which I will recommend you to read in details in the textbook. I will just describe what it is, and details you will find in the textbook, since we don't have time to focus on each topic during lectures. And that's why let me share the screen. Wait, maybe I also need to switch my camera. Then I will be able to write something when necessary. Share my screen. Okay, so first of all, I strongly recommend you to read in the textbook Higgins Principle. So this is geometric construction for using knowledge of an earlier waveform to determine the position of a new waveform in some time interval. So the principle is based on the following. So we have some, let's call it old wavefront, and each point at this old wavefront is considered as a source of spherical electromagnetic wave, like point source of spherical wave, which is spreading in the medium with the speed of light. In our case, since we are talking about light, so in case of free space vacuum, this speed will be equal to the universal constant c, and at some point, after some time interval, the new front, new position, like position of the new front, will be defined as the tangential line passing through these spherical waves. And these spherical waves are called wavelets. So they propagate through the medium with a speed characteristic of waves in that medium. And after some time interval, the new position of the wavefront is the surface tangent to the wavelets. So this is the fundamental concept which stands behind this Higgins principle. And by using this approach, it's possible to derive equations which we wrote for the reflection and refraction of electromagnetic waves or light at the interface between two mediums with different optical properties. So please read in the textbook about this concept. Also need to work with total reflection. So at some point there is a condition, special condition, when all light which is reaching the interface between two mediums will not will be reflected, but nothing will be transmitted. So it's so-called total reflection condition. So please read also in the textbook on this topic, and cover one more topic, which is dispersion of light. So we introduced during last lecture the concept of index of refraction. However, we didn't specify at which specific wavelengths this number we take. So the properties of different materials, they cause the frequency or wavelength dependence of this index of refraction. For different materials, this spectral distribution of index of refraction is different and unique for specific material. So that means that index of refraction depends on wavelengths, and different wavelengths will be refracted at different angles because of different value of the index of refraction. And that causes like splitting of white light into its components, different colors. So please read in details about light dispersion in the textbook. So now we will go to the main topic of our lecture. It's image formation. So let's take a look at this slide. And first we consider a flat mirror. So here we have in point O some point object. And in order to know how the image of this object will be formed by this flat mirror, we need to go through the analysis of light rays following the wave under reflection model. So in other words, we just pick up number of light rays which are emitted or reflected from the object. Then they reach the surface of the mirror, and according to the law of reflection, they are reflected from the mirror. So what happens here that we see that these reflected rays, they diverge after reflection, so they go at different angles and kind of deflect from each other. And if we extrapolate these reflected rays from the surface of the mirror towards their interception, we will get some point I, which is actually the image of our object O. So this distance from the object O to the mirror is like named P is the object called object distance, and this distance from the mirror to the image is, which is named as Q, is called image distance. So all images are classified as real and virtual. So in particular, here for this example, we have a virtual image. So let us explain what it means. So real image is formed when light rays pass through and diverge from the image point. So they need to go through the rays of light, the image point, and diverge from this image point. Keep this in mind. Then virtual image is formed when light rays do not pass through the image point, but only appear to diverge from that point. So this is exactly what we have here. We see that light rays, they do not pass through the image point, but they appear like they diverge from this point. So of course we don't have light rays here behind the mirror because mirror reflects all light rays. However, for the observer, it appears like these rays diverge from this point. That's why this particular example, we have virtual image, and what is necessary to know that all images formed by flat mirror are virtual images. It comes from the geometry and principle of functioning of this mirror, flat mirror. Okay, now let us talk a bit more what principles we use in order to build the image of some extended object. So usually, well, in order to build the image, we need to use, like, select two rays and see where they will intercept with each other. So in this particular case, on the right side, we have some object with a height h at some distance p from the mirror. Then we can consider just one highest point of this object, which is point P, and consider two rays. One ray goes perpendicular to the surface of the mirror, and another will go at some angle theta. So this one, the first ray, which goes perpendicularly, it will be reflected backwards. So we have incident ray and reflected ray. The other ray will be reflected according to the rule of reflection of light rays. These angles will be equal. So we know at which angle the reflected ray will be going. And now, if we extend reflected rays first and second towards their interception, kind of behind the flat mirror, we will get this point P prime, which is the interception of the reflected mirrors, and that is the image of point P. Means that here will be our image of all our objects, since point P is the highest point of the object which we consider. So the height of this image will be h prime, and for the flat mirror, this height is height of the image is equal to the height of the object. And another important parameter which we need to introduce is lateral magnification. So let me maybe stop sharing for a second. And this magnification M is equal to the ratio of linear size of the image to the linear size of the object. So in the case of flat mirror, this magnification will be equal plus 1. So why 1? It's clear because these heights of the object and image are the same, and this plus stands for the fact that the image is upright. So means that the orientation of the object and its image is the same. So it's not flipped over. If it is flipped over, we will consider some other cases later, then there should be minus. So, and also another important thing, if we consider these two triangulars, right angle triangulars, they are like identical, and that means not only height of the object and image are equal, but also the distance from the object distance P is equal to the image distance Q. So now let us proceed further with the more interesting examples and cases, which are images formed by spherical mirrors. So these mirrors have the shape of a section of a mirror, and there are two possibilities. First one is called concave surface, concave mirror, when reflection happens from the inner concave surface of the spherical mirror. So this is the first example what we will consider, and then we will go to the other one. So there are certain parameters which we need to know about spherical mirrors, and that is the radius of this curvature. Curvature center C is located on the line. So this line called principal axis is going through the center of the curvature of the mirror through the center point of the mirror. So this is principal axis and kind of important feature of spherical mirrors. So if, for instance, we have some point object and two rays are going from this object towards the mirror, they will be reflected and intercept. So if this object is located on the principal axis, they will also intercept at this principal axis. Here we will have some the image of this object and this image will be real as opposite to the previous virtual image because reflected lines, as we gave the definition, they go through, you see these two reflected rays, they go through the image and diverge from the image, literally, so not appear as they diverge from the image. So that is the feature of the real image formed by this concave spherical mirror. So let us talk about the formation of images with such, like in more details, formation of images with such concave spherical mirror. If the object is located at distance p from the center point of the concave spherical mirror, and the curvature also is known of this spherical mirror, which is radius of this circle defined, which defines the curvature of the mirror. Then we can build the image. So if these two parameters are known, we can build the image which is formed by this spherical mirror. So we consider again two rays which originate from the highest point of the object. One goes to the center point of the mirror and hits the mirror at some angle theta. According to the rules of reflection, it is reflected at the same angle from this point. And the other ray is considered, which goes from the top point of the image perpendicularly to the surface of the mirror. So it will be reflected backwards, and the interception of these two reflected mirrors will give us the image of this point, the highest point of the object. So this is the image of whole object. And this is again the real image because reflected rays are going through the image and diverge from the image. So now let us consider large red right triangular, so which is filled with red color. So this is this one, and the angle theta, like tangents of angle theta, can be defined as ratio of the height of the image, of the object to the distance from the object to the mirror. And from other point of view, we can consider the yellow right triangular, and here the same angle theta will be defined as like tangent of theta will be equal to the ratio of h prime, which is the height of the image, to the image distance q. Here it is necessary to underline that the image is inverted, like flipped over in comparison to the object, and that's why this h should be taken with minus. So let us go to the slide where I can write. Let us write this down. So we have from the large red triangular tangent theta is equal to the ratio of h to p, and tangent theta is equal to minus h to q. So now, based on the fact that these two angles are equal to each other, we can write that the magnification is equal to the ratio of h prime to h, like height of the image to the height of the object, and that is equal to minus q divided by p. So that is the definition of magnification of this concave spherical mirror. Let me share this screen again. So another option which we can go for is to consider these two triangulars, yellow and green. So from the green right triangular, we see that tangent of this angle alpha is the ratio between h prime and this distance. So this distance is defined as the difference between radius of the curvature and image distance. So we can write that tangent alpha is equal to minus h prime divided by r minus q. And the same for tangent alpha, but already from this yellow triangular, we can write that this is oh, sorry, not from yellow. We consider a small red triangular. We need this alpha angle, not theta. So from this small red triangular, we have ratio tangent alpha will be equal to the ratio of the height of the object to the distance between point O and C. And that is the difference between object distance P and curvature radius R. So now let us write this down, and then we will have opportunity to derive the mirror, so-called mirror equation. Stop sharing. Now we can write first, which we did from the red triangular tangent alpha is equal to minus h prime divided by r minus q, and the same angle tangent alpha will be equal to h. Now we have positive h because this is the object, not the height of the object, not height of the image, p minus r divided by p minus r. So taking this into account, that this alpha is the same, we can write that h prime divided by h, technically this is magnification, is equal to r minus q divided by P minus R. And since it is magnification, well, actually here we forgot minus, we can equate this part and this part. So it will be R minus Q divided by P minus R, and this is equal to Q divided by P. So from here we get the one of the forms of mirror equation, where we have 1 over P plus 1 over U is equal to 2 divided by R. So this is the mirror equation. And what does it tell us? That there is a direct relationship between the object distance, image distance, and curvature of the mirror. So if we know two of these parameters, we can easily calculate the unknown one, which is very useful while solving some problems or building some optical systems for particular needs. So now let us consider some specific case of light propagation. And what do we have here? So in the bottom part of this slide, if our object is located very far from the mirror and P is much larger than R, then rays are coming, like approaching the mirror from the object. They are close to parallel to each other. So if this happens, so we the reflected rays from the mirror, they will intercept in one point, which is called focal point, and this focal point is located at some distance f from the mirror, which is called focal distance, and this distance, focal distance, is equal to half of the curvature of the mirror. So that is very important parameter of mirror of this concave spherical mirrors, this focal distance, and it's important to that extent. It's like some unique feature of the mirror, like some unique parameter. And based on this focal distance, we can rewrite in a bit different form the mirror equation. So let us come back again to the slide where I write. So we see that, let's rewrite this mirror equation here, which we derived previously. 1 over P plus 1 over Q is equal to 2 divided by R. So let us mathematically show what we explained on the previous slide on this image. So if the distance P is very large, so the object is very far, then 1 over P approaches to 0. And from this part, we can write that Q, the image distance, will be equal to R divided by 2, and that is focal distance. So this focal distance is twice smaller than the radius of the curvature. So taking this into account, we can write the mirror equation in the most common form. So it will be 1 over P plus 1 over Q. It is equal to 1 over F. So this is most common form for the mirror equation. And keep in mind that for mirror, like spherical mirrors, focus distance depends only on the curvature of this mirror. That is not true for lenses, which we will consider in the future, because optical rays goes through the lenses and it interacts with the material of the lens. So it depends on refractive index of lenses. If we have different refractive index of the material from which we made these lenses, then the focal distance will be a function of curvature of the lens plus refractive index of the material. And in the case of the mirror, light doesn't go through the mirror, it's just reflected from the mirror, and that's why it is independent on the properties of the material from which this mirror is made. It just has to be reflective enough. So now we can consider another possible spherical mirror when reflection of light happens from the outer convex surface of the mirror. So in this case, the derived mirror equation is also working. However, we just need to keep in mind some features of this convex mirror and be very careful when we build the images of different objects. So, for instance, if we consider two rays from the top point of our object, one will go perpendicularly to this reflecting surface, so it will be reflected backwards. Another goes parallel to the principal axis, and the reflected light will appear coming out from the focal point. So if we extend now these reflected lines, reflected rays towards the interception, we will get the image of this top point of our object, and here will be the image of all our objects at some distance q from the center of the mirror. Since these reflected rays do not go through the image point and they just appear to diverge from the image, this image is virtual. However, it's not inverted, so it's upright. And there are certain rules with the signs of object distance, image distance. So for different cases, we need to be careful with the signs because that will have an impact on the result, which we will get when we use this mirror equation. So here is the table, and discussed some all possible combinations. So for instance, for object distance P, it is considered positive when object in front of the mirror. So we have real object. Then negative when object is back of the mirror, virtual object. So we will consider this concept of virtual object a bit later when we discuss images formed by lenses. Then we have, but so far we had only positive P because all our objects were in front of the mirrors. Then image location Q. If we have image location in front of the mirror, it's called somewhere here, for instance. It's called real image, and this distance is taken as positive. If it's in the back of the mirror, virtual image, then distance Q is taken negative. Image height H prime is positive if image is upright. So this case, image is upright, and negative when image is inverted. So in previous example, when we had image here, but it was inverted, then H prime should be taken as negative. Focal length and radius. So positive when mirror is concave. So when reflection happens from the inner concave surface of the sphere mirror, and negative when we have convex mirror. So for instance, in this image, we have convex mirror, and this focal distance, the distance from the center of the mirror to the focal point, will be taken as negative. Magnification also is taken positive if the image is upright, and negative if it's inverted. So it actually reflects the sign of the image height. So with these rules, you should be very careful, because if you substitute wrong sign in the mirror equation, then obviously you will get not correct answer. So I mentioned that it is necessary to have two rays in order to build the image of an object. However, usually it's good to use 3 rays, and with 2 we build the image, and with the third ray we kind of double check if everything was done correctly. So-called ray diagrams. So here I would like to share with you with some examples. When we build such ray diagrams, we usually pick up 3 rays. So ray number 1 is going from the, so all of these rays are originating from the same point of the object. And this ray number 1 goes parallel to the principal axis. On all these images is shown that so there is also the rule if the object is closer to the mirror as the focal distance, it should be taken into account, or it's further from focal distance, but those are some details. The main concept which describes the 3 rays which we consider is first ray goes parallel to the principal axis. Then when it's reflected from the mirror, the reflected ray will go through the focal point, which is located on the main, like this principal axis. So if you see this first blue ray goes parallel, then it reflected and goes through the focal point. The same happens here. It is reflected and goes, this extension goes through this focal point located behind the convex mirror. Then number 2 ray, which we consider to build these ray diagrams, this ray is going through the focal point, and when it is reflected, it's kind of opposite story to the first ray. It is oriented parallel to the principal axis. So we have here the same picture. It goes kind of appears to originate from the focal point, then reflected ray is going parallel to the principal axis. Here is the same. If it appears to go through the focal point, reflected ray goes parallel to the principal axis. And the third ray is that one which goes through the center of curvature at the distance r, which is radius of the curvature of the mirror. So in this case, it will hit perpendicularly the surface of the mirror and will be reflected backwards. So the same picture here, if it goes along this line, which connects the center of the curvature with the top of the object, will be reflected, and then it goes just in the opposite direction without changing the orientation, like angle. Here, if we pick up this ray number 3, which appears to go through the center of curvature of the convex mirror, the reflected ray will be also in the same will has the same orientation, just will go to the opposite direction. And with 2 rays, we already can build the image, because the interception of this first and second ray will give us the image. But with the third ray, we can always double check if it also intercepts in the same point as first 2. And in that case, we are 100% sure that our image is formed correctly. Okay, this is pretty much everything what I wanted to tell you during this lecture. We will continue on Friday with the image formation in lenses. Yeah, sure. You have some questions?
Hello. So this topic was in the volume 3 of the book, yes? This was a chapter 1, yes, topic.
I'm not sure exactly.
On this lecture, I mean.
Yeah, so it goes, this volume should be light and optics, and we just started it on.
Okay. One more question. What do you think is the best way to prepare for the upcoming midterm? Is it enough to just read the book and do some exercise on that?
Well, I think if you do
I just want to
properly, which requires to solve quite many problems per week, that is one of the ideas since we have this remote studying experience. I think so many
Yes.
problems is one of the way automatic preparation for the midterm. I would definitely recommend read through the textbook and maybe watch some videos of some topics which are discussed during lectures and which maybe are not so clear for you. Because one thing is to practice with solving problems, but you definitely want to have an idea where these equations are coming from. That is a big deal, like understand physics, not only just automatically use some equations to solve problems. But since we evaluate nowadays only by solving, like your ability to solve problems, so definitely solving problems, practice in solving problems should be top priority, specifically in those topics which are going to be covered during this midterm. So double check. There are 4 topics, four chapters on the textbook which will be covered.
Okay.
Yeah.
Understand.
Aside from that, yeah, just can also advise you to be careful with the internet access. Try to be sure that the power is not going to be switched off and internet access. Also log in into Longkappa as early as possible. Don't wait to the last moment, like maybe 30, 20 minutes prior the start of exam, because already had some experience earlier that students complained there were some issues with logging into the system at the beginning of the exam. So in order to avoid this, try to do it earlier.
Okay. I understand.
Okay.
Thank you very much.
Yeah. See you on Friday. Have a good evening and take care. Bye-bye.
You too.